Hello, everybody. Welcome to another session of the Polkadot Deep Dives. And today we have a really nice topic prepared for you. It's called Try Runtime. Some of you may have heard of it. Others may not have heard of it. Either way, it's a critical piece as a frame developer, as a Polkadot developer. Try Runtime is crucial. So the agenda today, we're going to talk about like what is Try Runtime, what exactly is it, right? And uh, Try Runtime is I'll let you know that with my personal journey with Try Runtime, it wasn't the easiest thing to understand of like what it is. So I hope that with this presentation, we took all the complexity, at least we tried to take all the complexity out of it to present to you, to frame it in a simple way. Okay, so I hope that we achieve that. Please let me know. So we're going to discuss what is it. We're going to talk about some high-level features. It's got a lot of features. We're also going to then drop down and actually talk about what's a typical flow, how it works. And then Bernardo has a deep dive demo for you set up where we're actually going to go through a try runtime example, which is really, really useful. Okay, and then at the end, we'll open it up for questions. By the way, my name is Bruno. If none of you know me, I'm a developer, an engineer at Parity, and Bernardo, which will be presenting the demo, is also an engineer at Parity. So let's get started. Try Runtime, Substrate's ultimate testing framework for the power users. That's a pretty hefty line. That's actually, I took that line from the documentation. It's at the very top. I can show you later. It's a testing framework and it's ultimate. So that means there's a preface there, that little paragraph, that in order to really use Try Runtime, it's expected that you have somewhat of an understanding of the client and of the runtime. So how does the client work? How does the runtime work, right? What is the runtime? What is the client? What are the interactions between the client and the runtime and back and forth? Okay, so if you don't know what that is, I recommend there's great resources out there to understand the interactions there. Another prerequisite for this presentation and for really finding Try Runtime useful is to understand the upgrades, the runtime upgrades, how runtime upgrades work, perhaps even do a runtime upgrade yourself, as well as storage migrations. Okay, so these will be key elements to as part of the Try Runtime workflow. All right, so what I want to do is we're going to look at a couple of definitions of Try Runtime and slowly get into it, slowly step into it. So the first definition here, it says, the Try Runtime command line tool enables you to query a snapshot of runtime storage using in-memory externalities data structure to store state. With this tool, you can write tests against a snapshot of the runtime state before going to production. So I want to highlight here that it's a tool. In the previous slide, we said it's a framework. In this slide, we're saying it is a tool. All right, it's both a framework and it is a tool. There is a CLI. And this tool, you can think of it, it lets you, as a developer, as a frame developer, it lets you test your runtime in various ways. And it lets you test your runtime in detail with a high degree of control over the environment, the state, right? So let's look at one more definition. Try Runtime is a CLI and a set of custom runtime APIs integrated in Substrate that allows you to do detailed testing, including running on runtime upgrade code of a new runtime on top of a real chain's data. Okay, I like how it says including there, because there's more features that Try Runtime has, but this is one of the main features. Try Runtime has a lot of features. We'll try to discuss like the top ones, and then we'll give you resources to go deeper if you'd like. But even here, like if we think about it, like why would this be useful to test migrations for runtime upgrades, right? Let's think about that. Like if we think like, what are we doing with migrations, right? Like what if a migration goes wrong, right? What can that lead to? That could lead to your chain stalling. That could lead to some unintentional consequences. So this is one of those pieces of like, if you're writing a storage migration as part of your runtime upgrade, you want to make sure you test it properly. And there is no better way of testing it against actual real chain data, right? And Try Runtime allows you to do that. So a typical flow of like how Try Runtime works, you could say like pretty like hello world example here. It's like, the idea is like step number one, you connect to a live chain. Step two, you scrape that chain's state and you put it inside of a test externality, which you can then use to call specific runtime APIs to test your runtime, to test, did my migration, work as expected. All right. So this is really useful once again, because you can rest assured that like you just ran your upgrade locally, you tested it against real chain data, and it worked. You have some checks in place to make sure, okay, this is my state before the upgrade, and this is my state after the upgrade, and they're aligned. This is what was expected. And that's a great reassurance. It helps you sleep at night, because then when you push that upgrade to production, you've tested it, right? It's a great tool for that. So one thing that I want to mention is like the idea of taking state of a live chain and putting it inside of a test externality, right? If we think of state and substrate, we think of like key value pairs. And if we think, somebody said Polkadot devs don't sleep in the chat. Yeah, I can see that. Yeah. But if they do sleep, maybe they'll sleep better, right? The quality of sleep may be better here with Try Runtime. So when we're working with Try Runtime and we're taking state and we're pushing it into test externalities, we can actually pick what we want. We can pick the full state of the live chain, all the key value pairs. Or if we want, like if that's not critical for what we're testing, we don't need all the state. We can pick specific pallets, the state from specific pallets or prefixes or keys, okay? With Try Runtime, you're allowed to, you have that feature that you can select the key pieces of state that you'd like to go into test externalities. So a little recap here, a little review, right? We all know, like at least we should know if we're working with Try Runtime, that the client communicates with the runtime. How does the client communicate with the runtime? Via runtime APIs, right? And how does the runtime communicate with the client? Via host functions. So the runtime communicates with the client via host functions. And where is the storage? The storage is in the client, right? So if you're working with Substrate, you may know that the storage is in the client, and there's this thing called externalities. That's like, you can think of it as like an abstraction layer around the storage, around the data of your chain that's in the client. And the runtime accesses these host functions that are in the externalities, right? And so one example of this externality is test externalities. The idea is that we have this layer of test externalities that we can access that will have our live chain state that we can write unit tests against, essentially, right? I mean, that's pretty cool. Imagine like with Try Runtime, you could get Polkadot state or your parachain's live chain state and write unit tests against that state, right? That's pretty cool. how this happens, like under the hood, under hood, there's something called remote externalities, which that's what takes the state of the live chain and injects it into test externalities. What you're seeing there on the screen, it's a code snippet. It's an example of how remote externality works under the hood and how you can use it. So you can see literally there that we're specifying like an RPC node there, Polkadot, and we're saying we only want specific pallets, the state of specific pallets. So in this case, pallet A, pallet B, pallet C, and some random prefix. All right. So this is going to be, an RPC request. So depending on the amount of state or what type of state you're getting, it could be slow. So, I mean, take that into account, right? You only want the state that you want to test against. Remote externalities is what allows you to specify the different pallets. You can, like mentioned in the previous slide, you can inject like custom keys. You could even inject custom key values. This is where you can kind of like customize like what kind of state you're going to be pulling in into your test externalities, right? So all of this coming together, we can say like with Try Runtime, the idea is that you download the state of you take the state of some live chain, perhaps Polkadot or your pair chain. And with the remote externalities, right, it will write that into a test externalities. So if we're testing some runtime upgrade, in this case, it'll overwrite the code, the well-known key called code, with some given wasm blob, the new one with the new changes, right? And then we can test that with some runtime API call, perhaps like something like unruntime upgrade, right? And we're testing it against real chain data. So for example, I keep saying testing, right? Before and after. So how you test like on runtime upgrade, right? On runtime upgrade is where you'd write your migration, right? So the migration, when you do the runtime upgrade, the migration will take place. With Try Runtime, there's two hooks that are pertinent to like on runtime upgrade. One is pre-upgrade, and you can see there on the screen. What's interesting about that code snippet is that there's a feature flag there. You can see it says the Try Runtime feature flag. So we're going to show you, but when you're enabling Try Runtime, these feature flags in the runtime get enabled. All right. So there's a pre-upgrade hook where you can run some checks on your state, on your blockchain, on your runtime before the upgrade. And then on runtime upgrade kicks off, does the migration, right? Does the upgrade. And then there's another hook called post upgrade where you do some checks after your upgrade, after your migration. And what's interesting, how these two hooks, they actually work together. I don't know if you noticed, but the first hook pre-upgrade, there's a result of vector U8, right? So it'll return some data, like whatever, logic you have in the pre-upgrade. It will run through that logic, and maybe you want to return some data. That data gets passed in as input to the post-upgrade. You can see there the parameter state vec-u8. So it's really useful for you to do like some check in the pre-upgrade, and then the result of that, you can pass it into post-upgrade to make sure that the state is consistent how you expected it. Okay. Try Runtime also has some other features. We're not limited to like the unruntime upgrade, the pre-upgrade hooks, and the post-upgrade. There's also another hook that this would go inside of your pallet hooks inside of your pallet. It's called TriState, and that hook can be used if you want to test that your pallet state is consistent and correct. So you can write some checks inside of TriState. Other features that come with Try Runtime, there's some subcommands. You can see there it says on runtime upgrade. That's the one we just discussed. There's also another feature called execute block, which is really cool. The idea is that you could take a specific block, let's say, from the live chain, and you can execute it against your state, right? So depending on the use case, once again, there may be like multiple use cases here, but you can think maybe there was a block in the past that produced some type of bug based on the logic of your chain, right? And so you're pushing a runtime upgrade that should resolve that. So as part of your test, you want to test your upgrade against that block that created the bug, right? So you can use execute block. There's also off-chain worker. So that executes the off-chain worker hooks of a given block against the state that you specify. And the other one is follow chain, which is pretty cool. The idea there is that you're testing chain progression. So perhaps depending on your upgrade and your storage migration, you run your upgrade, you run your migration, and you just want to make sure that your chain is progressing as it should be. All right, and then that's where follow chain could be useful. It'll continue following the chain's finalized blocks and applying extrinsics, and that could be useful depending on your test case. So let's talk about a typical like try runtime, like a typical flow, right? Now that we know like some of the high level features, let's get a little bit more concrete and give you some steps of like how one would go about this. So step one, as we discussed, the idea would be you have some live chain, whether this be like Polkadot or your parachain, you have some live chain running, right? This is the chain that you want to scrape its state. And step two, you're going to write your migration, right? You got to write your storage migration. So we're going through a flow of like on runtime upgrade, right? This is the on runtime upgrade typical flow. So you have your storage migration, you wrote that down, it's in your runtime, the code is there. And you also have your checks in place, right? Your pre-hook and your post-hook. So you're going to do some check before the upgrade, before the migration, and then you're going to do some check after the upgrade, after the migration. You also want to make sure that you have some logs in place in your pre and your post, as well as in your migration, so that when you run your test, you can see the logs and all the important information that you want to see, that everything succeeded. The third step is you're going to compile that node that you scraped the chain data that you're going to compile the node that you script the chain data, but the one that you wrote your migration on. Okay, and you're going to compile it with the try runtime feature. So there's the line right there, cargo build -r features try runtime. And when you do that, you're going to get a binary with the try runtime CLI, the tool. Okay, that's going to be part of that. And when you compile a node with the feature try runtime enabled, all those feature flags that I mentioned that are in the runtime, the try runtime feature flags, they're going to be enabled. All right, so that's going to make it so the pre, the post, all those hooks that we discussed will be active. We then, after we've compiled that, we're going to take the binary, we're going to copy that binary that we just compiled. We're going to rename it to something like node try runtime because it's got the try runtime CLI in there. And it also has all the changes, right? The storage migration, the runtime upgrade, it has everything in there. So we're going to copy that and we're going to execute the binary with try runtime. So you can see there, I'm going to enable the Rust logs and I'm going to execute the node that I just compiled with the try runtime command. And I'm going to pass in the WASM that has the runtime upgrade and the storage migration and the checks. And I'm going to pass in the subcommand on runtime upgrade because that's what I'm testing. And with try runtime, you have to say checks pre and post so that those pre and post hooks will run. And then you specify the chain that you're going to scrape the data from. In this case, I'm using localhost because in this example, I have the live chain running locally. Okay, but this is where perhaps you'd have an RPC. All right, and RPC to Polkadot and RPC to your parachain. And you want to make sure on that side that you have RPC enabled on that node and you may want to tweak the flags. There's certain flags that allow, how do you say, like, it may take some time to pull in that state. And you want to make sure that your node that has the RPC enabled doesn't time out. Okay. The specific flag, it's in the documentation. I can't remember right now on the top of my head. But then you execute this command, and that will execute the try runtime, and it will perform the upgrade with the storage migration. It'll run the pre-check before the upgrade, and it'll run the post-check after the upgrade. And it's going to tell you with green check marks whether it succeeded or not. And you're also going to get the logs that you wrote. Okay. So that's try runtime in a snapshot, in a nutshell. There are some additional features. I want to show you the documentation. So that first link there, it's really well documented. So perhaps I can show you that before we switch it off to Bernardo for a demo. There's also another talk there that I have listed at the end. And that's a YouTube talk, and it goes into try runtime, perhaps a little deeper on other aspects. So that might be interesting for you. But that's it in a nutshell. So let me just show you the doc. So this is the Try Runtime CLI in the Substrate Rust docs. I really recommend it. It's a great resource, and you can see it's got a lot of the information that we covered, and it's really thoroughly documented. So it's a great starting point to get started. And oh, here's the RPC flags that I mentioned. Okay. So there's some best practices, the pre and the post hook that we discussed, TriState, checking state consistency. There's even some examples on there that you can test yourself. All right. So with that said, I'm going to hand it off to Bernardo for going over a demo. He prepared a demo for you. And hopefully with all this context, the demo will be super helpful for you. All right. Thank you.
Hi, everyone. So I'm Bernardo, and today I'm going to present a live demo of Try Runtime in action to give you guys an idea of how does a hands-on experience with this tool looks like, right? So the context for this demo is, I guess at this point, some of you might be familiar with the substrate node template. It's a very simple substrate node that it just provides some basic functionality. And we're applying some changes to the runtime on this template. And I made it a very simple change so that it's a good example to teach the principles. But obviously in the production scenario, the changes would be a little bit more complex. The key point to have in mind here is the concept of scale encoding and how different types are encoded inside the runtime. So on this substrate node template runtime, I'm changing how the balance of an account is encoded, right? So originally, we were using 128 bits, but now we're using only 64 bits. And this changes the scale encoding of the balances, and they're not compatible when they're in the runtime. So if we simply change this in our runtime and we perform a runtime upgrade, and we don't address the fact that we changed the scale encoding of a very important type in our runtime, things will break. This runtime upgrade will basically break our chain. So this is the main piece of information that is meaningful for our demo, is the fact that I'm changing the balance from U64, sorry, from U128 to U64. And these are just some other changes that I need to apply so that the compiler is happy and we're able to compile this runtime with this new type. So I'm gonna show you a little bit of what needs to be done extra on top of that modification of the runtime, right? Because we need to write a storage migration. And that is done. You can do that in two different ways. You can do it per pallet, or you could do it per runtime. And in Parity here, we're sort of phasing out the first approach where you do it per pallet. So I'm going to show you the most used approach nowadays, which is you just go to your runtime source lib.rs file, and you need to add some extra code there. And well, we're changing the balance type, and that means that two pallets are going to be influenced by that. Basically, the balances pallet and the system pallet. The system pallet keeps a lot of data about the accounts. So we have this account info type on frame system pallet, and on the balances palette, we have this account data type. And so the most important part of this code is this new struct that I declared here, and the fact that it is presenting the runtime update trait. And this signaling that we're performing a storage migration. As soon as there is a runtime upgrade being enacted, we want to make sure that this also gets executed, and this code is effectively the storage migration. So what is this code doing? We're basically just we're iterating over all the accounts. So basically, frame system has this account storage item, and the translate function is basically just iterating over all items, and we're modifying it, making it something else, right? We have a clear here. We specify what kind of change we want to every of this step. So closure, we have access to the value. So whatever accounts used, we have to that. For every old value, we're going to create value. And we're changing the accounts. So we have this helper struct here, which is just basically telling the compiler, hey, this is how this is used like. All the balances here are 128 bytes, 128 bits. For every value, thinking that, well, this is a database, right? So we have keys and values. We don't really care about the keys. But for every account, we have an entry on this database, and we're iterating over all the. So when it comes to account info from the same frame system palette, we don't really care about these fields: consumers, nonce, providers, sufficients. We're just using the old values, right? But when it comes to data, we need to update them. And we're basically using this saturated into method that it's basically a safe way to do this conversion because we're avoiding overflows, potential overflows here. So we're bringing this straight into scope, and this is where the translation is being done. And we have just a helper counter here, so we keep track of how many accounts we perform this migration on. And so basically, this is the storage migration. It returns a weight, and I didn't really do this for this demo. It should be done in production because, well, this is going to be executed in a block, and blocks need to keep track of how much weight is consumed by every operation. This is effectively going to return 0, and I just don't want to really spend a lot of time here because benchmarking is a little bit outside of the scope of this session. But please do research what benchmarking is, what weights are, so that your runtime migration is returning the appropriate weight here, and your blocks are still sane in terms of how much weight is consumed by every operation. And then here we have two other helper functions, which are just one is executed before the upgrade, and the other is executed after the upgrade. And it's basically a sanity check. It's so here in this case, iterate over every account before the upgrade, and I count how many accounts there and what is the overall of balances. Then I encode it, and the output of this function is the input of this function. So the post-upgrade basically doing the same thing. Just count how many accounts there are, what their sum, all the balances, and do an assertion to make sure that the same, right? And if they're not, things are going to break, and I know that there's something wrong with my migration. So this is the code that I wrote for the storage migration. And I have a few binaries here on my machine that I prepared for this demo. So basically, I have one node template that is a node without any modifications, running the old runtime. And you can imagine this is synced with the live chain, right? So I have an RPC node on my machine that has the same state as whatever chain is out there in the world. Maybe it's a testnet, maybe it's a mainnet. The point is that the state is the same because it's synced. I have another binary, which was built with the Try Runtime feature, right? So it has this Try Runtime tool embedded into the executable. And I have two WASM blobs. They're both candidates for the new runtime. So both of them have this modification that I showed you here. But one of them does not have the storage migration. One of them does not have this code. And one of them does have it. So I want to show you the consequences of not doing a storage migration and how Try Runtime is going to help you figure out what's going wrong. So here are the 4 artifacts that I just talked about. 2 executables and 2 WASM blobs. This is my node. It is running, and it is synced with the live chain. So I'm going to run this command, which is I'm invoking the client with the Try Runtime. And I'm using the Try Runtime subcommand. I'm specifying the runtime with without the migration, right? So this WASM blob was compiled with the new runtime, but there's no storage migration in this wasm blob. And then we're calling the on runtime upgrade subcommand, and we're telling it, hey, just look at this local node for the state of the chain, for the remote externalities. And we run it, and we get some logs here. And basically, first we have some logs from the remote externalities. So basically, we're populating the state. We have a storage root here, and we have the spec version. So the original spec, the old runtime, is 100, and then we have the new spec version, which is 101. So that is the spec version of the new runtime. We have a few debug logs here that are not that meaningful in the context of this demo. Because like I said before, you could do a runtime migration. You could do that code for the runtime, for the entire runtime, or you could do it per pallet, right? And if had we written any storage migration per pallet, it would show up here. But we didn't do any storage migration, and when we do it at a runtime level. So these debug logs are not that meaningful. Here we can safely ignore them. And the main line here, the most meaningful line here, is this error line, and it has an error with the root, right? Because things are breaking. This runtime upgrade. If we did this runtime upgrade without the storage migration on a live chain, we would break that chain because the state root would not match what the client calculated and the result of the new block. They're not matching. So there's a problem there. And happily, we have Try Runtime as a tool that we can sort of dry run this and see, okay, I'm still not ready. I still need extra stuff before I do this runtime upgrade. And we're illustrating this here with the lack of the storage migration, because here we're using this wasm blob. So now we can do a very similar command, but this time we use the wasm blob with the storage migration. So it's pretty much the same command that we did before with a new wasm blob. And now we're also calling this checks option with pre and post, just to make sure that these two functions will be executed. I knew that it was going to fail the previous command, so it wouldn't really make a difference to have this parameter here. But now that try runtime is going to be successful, this is more meaningful. And the rest is all the same. So we run it, and all the remote externality logs are pretty much the same as before. We have here the spec version too, but now we have these two lines, which are a little bit more meaningful. So this first line, it's indicating that we migrated 4 accounts. This line is based this line, right? After we have on upgrade, we have each for all accounts. We have counter here, and this is a node template, so we have 4 accounts, which is Alice, Stash, Bob, Stash. And so we made all these 4 accounts. Now they're about coded with 64 bits only. And we also have this line, which is the upgrade. It's this line. And it's sort of sanity check that, well, we iterated over all the accounts, and we're seeing how many accounts there are, what is the sum of all their balances, and they're matching. And we get this line here that sort of indicates that. And we have nowhere message. So now, because we wrote storage migration and we're using Try Runtime, we have a little bit more confidence that this runtime upgrade, when we finally execute on our live chain, we're not going to break the chain. This runtime upgrade is sane and it is appropriate for the changes that we aim to do. So that is all for my demo. I hope I was able to illustrate some concepts. I apologize for technical difficulties.
Thank you all. Thank you for being a great audience, and looking forward to the next session.